Hi everyone, I'm Davidson. I'm working on Utreexo, and I'm here to talk about Utreexo and Lightning, which is something that I've been really interested in lately. So anyone here doesn't know what Utreexo is? Raise your hand. Okay, so I have some people. So I'll explain what Utreexo is. So the agenda today is basically we'll look at why Utreexo is useful for Lightning, how it works, but I'll not explain the algorithm in depth. I'll just like say the parts we need to understand how to integrate with Lightning, and then how we could integrate with Lightning. So I'm a Bitcoin open source developer. I have a grant by Vintium, a Brazilian nonprofit that supports Bitcoin developers. I'm maintaining something called Floresta. I don't know if you guys heard of it, and also Utreexo, which is the Rust implementation of Utreexo. My PGP key, if you're into this stuff, and my GitHub, which is usually where I post stuff. It's my name, basically. So why would we do that? That's the obvious question. Lightning nodes, they are required to fetch UTXOs for every channel that they receive GOSP for. So every time you receive a channel announcement, you need to look up some UTXOs. And for that, obviously, you need the UTXO set. But that's kind of heavy, like it weighs about 12 gigabytes nowadays, and it gets out of hand when it comes to I/O. So we're seeing people talking about like using spinny drive for nodes. That's a big no-no. If you ever try this, you know that's going to take like months, because spinny drives are not good at random reads. So to alleviate that, we've got like Taj came up with Utreexo, which solves this problem. It's like an accumulator. I'll explain what that means in a moment, but it alleviates the problems that are associated with keeping the UTXO set. But for Lightning nodes, you still need to get those UTXOs, and with Utreexo, you don't have them. So we need some extra support from the Lightning side to actually support having those like those Utreexo nodes supporting Lightning nodes. And the project I work on, Floresta, it's a lightweight client. It can either be like fully validation, so you validate everything, you're just not keeping stuff, and there is some alternative trade-off methods. I'm not going to enter too much into them, but it's meant to be like the lightest Bitcoin client you can have, where it's still having great privacy and security. It uses about 300 megabytes of disk and 200 megabytes of RAM. So it's very lightweight. Last year I won a hackathon in Brazil for like a project where we ran that on a smartphone. So I have like an old smartphone, an old like 2018 smartphone. We ran on the smartphone. It was like nothing. The smartphone wasn't even like caring that it was running a node on this phone. So and everything is done locally, so you have better privacy, you have better security because you're not trusting anyone. Right now we use compact block filters for some information, but it would be better if you could use this like natively into Lightning. So Utreexo is a dynamic accumulator. That means rather than have the full like the full UTXO set, you have like a small version of it, like a small representation of it. How small is like less than 1 kilobyte. And whenever someone is trying to claim that some UTXO was in the UTXO set, you give them like they have to give you a proof that the UTXO was in the UTXO set. That proof is just a bunch of hashes, and as long as the proof is valid, then you are 100% sure that the UTXO was in the UTXO set, so you can accept that. With that, you change the trade-offs. Instead of like having big, fast SSDs and not using a CPU at all, if you ever ran a node, you've probably realize that the CPU is not the bottleneck at all. It's just like I/O, like going to the disk and coming back. With Utreexo, you're actually using the CPU, which is good because everyone probably heard about Moore's law, like hardware is getting fast, but I/O is not getting that fast. Like the capability of the CPU to go into the disk and back is not getting fast as CPUs themselves are getting. So we are using the part that it's actually getting better, and also bandwidth. We use extra bandwidth, but bandwidth is also getting cheaper, faster than I/O. So we are kind of moving the trade-off to the right direction, and we can do this cool stuff like running on the phone. So that's the trade-off for Utreexo. You're using a bit more CPU and bandwidth, but those are usually not the bottleneck anyways. So it's a better trade-off. Just to understand how this would work on Lightning, like I'm not going to explain the algorithms themselves, but Utreexo use something called forest on macro trees. So yeah, forest is just a bunch of macro trees. I think most Bitcoiners already heard of macro tree, but I'll show an example of what it means in the next slide. To prove something, you need to review the hash to recompute the roots. So you keep the roots, and someone gives you a bunch of hashes, and these hashes, you can use them to compute the root. This is an example. I want to prove 0, which is my Utreexo. I need to show 1 and 5, which are the green ones. And the nice thing about this is that the amount of hashes you need to review is logarithm to the size of the whole thing. So I have 4 leaves, so I need to show 2 nodes. If I have like 4.2 billion, I have to show 32 levels. So it scales logarithmic, which is one of the best scales you can get. And the proof is tiny, like it's very small. And every node is just a hash, like a 32-byte hash, so very small. And with that, I just like take 0 and 1, concatenate them, compute 4, 5, I compute 6, I have 6, I compare 6 with what I computed. If they match, the proof is valid. If they don't match, the proof is invalid. So this is macro tree. Utreexo is a bunch of those trees, basically that. And one cool thing about Utreexo, which is why we use Utreexo, some people actually ask that because there are fancier accumulators in cryptography, like the RSA accumulator. The nice thing about Utreexo is that you take the accumulator over there, and you get to this one. I'm not going to explain how the update algorithm works, but I do the operation like in the forest itself. It's just a bunch of pointers like being swapped around. And when I come to here, notice how the proof implicitly updates. Because over there, the orange node, like the 0, I need to review 1. Over here, I need to review 5. I didn't do anything for the proof itself. I just updated the forest itself. And then the proofs updates like implicitly. This is not the case for RSA. RSA, you need to go for every proof, one by one, and then recompute, like update the proof. It has to be updated. There's a paper, information theory paper, that shows that you cannot have a dynamic accumulator, so an accumulator that you update stuff, that doesn't update the proof. That's impossible. That's like information theoretically impossible. And the guy who wrote the paper wrote to Taj that Utreexo is like one of the best you can get, so it's kind of cool. But I do a bunch of like pointer operation or like file system operations, and I get to this side. And then the proof changed itself. And if I had like millions of Utreexos here, the proof for them would change, and I would not have to change, like to touch every single Utreexo. If I'm adding 5,000 Utreexos, I'll add those 5,000 Utreexos. And the other ones I had over there, I don't need to touch them. Like they are there. And whenever I need to prove something, I just look at the forest, because this is my tree. So if I want to prove 4, I need 5. That's basically it. I just look at the forest and just like walk up into the forest, and that's my proof. That's the proving algorithm. This is important because wallets can keep track of proofs more easily. If you have like thousands of proofs, thousands of Utreexos, doing it for every single Utreexo, every single block is not going to scale. It's terrible. But here, you don't do anything for the proof themselves. You just update for the accumulator to get it to the new state for representing that block. So Utreexos being spent, you remove them from the accumulator. Utreexos being added, you add to the accumulator, and that's it. This is way more efficient than using the RSA accumulator, for example. So, yeah, and one very interesting thing in Utreexo is that if you look at this one over here, notice that if I'm interested in 4, I don't really need 2 and 3. I only need 5 to prove that I have this Utreexo. I can completely remove from my local storage 2 and 3. If I ever need them, someone can give them to me. That will be part of a proof. So if someone is spending 2, they'll give me 3. So this will be part of a proof. If I don't care about neither of these UTXOs over here, I can delete them. I can just ignore them. And another cool thing about Utreexo is that the algorithm to change the accumulator, they only requires the number of leaves, the roots, what's being added, and what's being deleted, and the proof. So everything that's below the roots, I don't care about them. Everything that's going to change will be in the proof. So I can completely, if I want to completely remove everything here and you only keep 6, I can do that. And I can still update the accumulator locally, without trusting anyone. So these are cool properties that only Utreexo, the perfect macroforest that Utreexo has, and allows us to do some cool stuff. For example, you can have a node that doesn't have any UTXO at all, so it's just like the accumulator roots. That's the less than 1 kilobyte accumulator. It's like 900 something. You can have some of them, but not all of them. And if you have some of them, you can generate proofs for the ones you have, but not the ones you don't have. But this is fine, and this is what we'll use for Lightning probably. And you can keep all of them, and then you can generate proof for everything. But of course, that would be huge. You need a lot of gist to keep all the nodes in the forest. The interesting part is really you can keep some of them and not all. And this is possible because the inputs for the addition and deletion algorithm, they don't require those bottom nodes. Every node that we touch in the process will be in the proof. So we don't care about them. Another way you could do this is with compact block filters, which is a way to find transactions relating to some addresses or spanning some UTXOs. But it has some problems that you need to do a lot of calculations for every single UTXO you want to find. And in some high latency, slow network connections, it can hurt UX a lot. You need to wait a lot to synchronize the gossip. And there's more data to store. You need to store at least the filter headers. So it's not fun. It's not great. There are some wallets using it, like Zeus, for example, uses it. But I hear complaints about compact block filters, and for these specifically, they are not great. They are great for syncing wallet, but not really for finding UTXOs in the chain. So there are 2 ways I thought about this, thinking about how to implement this. There is what I call the correct way and the permissionless way. The correct way would be the most efficient way to do this, would be the most elegant, but require change to the peer-to-peer protocol, to the Lightning peer-to-peer protocol. So it needs to be supported by implementations. And there is the permissionless way, which is kind of trusted, but don't require any change to the peer-to-peer protocol. You can do that today. The correct way would be nodes, like Lightning nodes. They keep a partial forest. So if you only have some of the UTXOs, you have a partial forest with only UTXOs that represent channel out points. So you have, let's say, 20,000 channel out points, like UTXOs representing channels. You hold proofs, you hold them into your forest, but nothing else, just them. And whenever someone is syncing gossip from you, they request proofs for those UTXOs. So you download the proof, you verify them. If they are valid, you keep them locally. That chain is valid. You just keep going. And then if some other node is synchronizing, they learn about a new channel, they look at the channel out point, they request this to some other peer. Probably it's better to ask for the peer that gave you the channel announcement for the same peer. They will give you a proof. You validate the proof. If the proof is valid, you accept it. If it's invalid, you should not mark the channel as invalid, because Utreexo proofs are third-party malleable. So they could take a valid channel and make it an invalid proof for them. So I think the best way to do this is hang up on the peer, ignore the channel for now, and wait till someone else gives you the actual proof. So they will give you, again, the announcement for that channel, and they will give you a valid proof. And you'll just hang up on the other peer who is lying. So it's simple. You need 1 or 2 new methods, probably. I think it's good to make it separate from the channel announcement gossip message, because Utreexo proofs, they are batchable. If you take a bunch of individual nodes to prove them, you can like have overlaps in the forest as you move up, and those overlaps, you don't repeat them. If you can compute something, like let's say I'm proving UTXO A and B. In the proof of B, I can compute something that would be in the proof for A. I don't need to repeat that thing. So you can get proofs that are smaller than like the individual proofs. If I prove A and B separately, the proof may be bigger than A and B batched. So I think you can like download a bunch of channel announcement and then request like a batch proof that would save you some bandwidth. They're not like huge. A full block worth of UTXOs can get like 1 megabyte, so it's like thousands of UTXOs being spent. For a few UTXOs that you request in Lightning, won't be a lot, but anyway, you can save some bandwidth there with those overlaps. So here's the flowchart. You just channel announcements to peer B. Peer B, after they get enough channel announcements or some time has passed, send a get Utreexo proof, and then node A sends a batch proof to peer B, and they validate that and check if the channels are valid. And this is compatible with ZK proofs, because one problem with Lightning is that you have to link like one on-chain UTXO with your Lightning node. That is a security and privacy problem. Some people talk about ZK in this situation, so I prove that I have some UTXO with a specific value, like in a range, and that I prove that it exists, it hasn't been spent, but I don't tell you which one. You can use, there is an experiment using a Utreexo verifier inside a ZK prover. So you take that proof, like that Utreexo proof, like the hashes, and run the verification algorithm inside a Stark prover. So you have a proof that someone knows a valid Utreexo proof, basically. And with that, you know that the Utreexo exists, but you don't know which Utreexo is it. And I think it also works with OxyT, which is another scheme to do the same thing. You basically give a bunch of UTXOs, and you say, I know the secret image, like the secret key for one of those UTXOs. I'm not going to tell you which one. I'm just going to tell you that I know for one. So I think you can get like a Utreexo proof for multiple UTXOs, and then because you need to know whether the UTXOs that's given as part of this, it's called like a ring signature. You need to know that those UTXOs are valid. So the first part, which is I give you a bunch of UTXOs that are, one of them is mine, I can give you a Utreexo proof for those UTXOs for you to know that they are valid. The permissionless way would be to use something like ExpressSync, which is like, instead of you building the graph yourself locally, and that's slow and can take a lot of time, and while you don't have the graph, the other part, like the user can't really make payments because you don't know how to route stuff through the network. You also give Utreexo proofs for those channels that it's in the file there. Like I give you a file with a bunch of channels, and I also give you the Utreexo proof so you can check them. If they are valid, then you cache them locally, like your client. And you can keep them, and they, like I just validate them. And then for new UTXOs, like for new channels, I keep, like there are some specific UTXOs that can be Lightning channel. For instance, for now it's basically page written script hash. So I keep like the last days or like last 2 days worth of page script hash UTXOs, and if I see a channel announcement for them, for one of those UTXOs, I know it's a channel, I know the UTXO exists. After like some time, I can just throw it away. So I need to keep like a tiny cache of the latest page script, written script hash UTXOs to make the channel. So this can be implemented right now. It doesn't need any change to any spec of Lightning. It just needs like the client to support it, but you're trusting the client that's giving you the file with all the ExpressSync information. So it's a trade-off. They cannot tell you what channel exists that there is no UTXO for it, because Utreexo. So it's actually improving. ExpressSync is something that exists today. This would be an improvement over what exists today. But they can lie to you by omission. So they can give only their channels and not like all the other channels that are in the network. So you only route through their channels. So it's kind of trusted here. And the correct way, it can also be only the LSPs. So we're mostly interested in like end clients like Phoenix and Zulz, so wallets used by final users, not the actual backbone of the network. And those wallets usually are linked to an LSP, like Zulz uses the Olympus LSP. So one thing we could do is have the LSP to implement something like this, and then the local wallet implement this. So the network core, like let's say the big nodes routing stuff around, they don't need to care about Utreexo, only the edges care about Utreexo. So only the mobile wallets and lightweight wallets that you run on your computer, they care about this, and the LSPs are the bridges. We usually call, like when you have in Utreexo, when you have like a network that doesn't speak Utreexo and one that speaks Utreexo, we call this a bridge node. We have those for mainnet, and we can have them for Lightning. The Lightning one, they are smaller because they only need to care about Lightning Utreexos, while the mainnet one, they need to care about all Utreexos. So it would be a path, because that wouldn't necessarily need change to the main spec. That wouldn't need widespread adoption for all implementations. It could be just like the nodes that make the edge of the network. So wallets and LSPs, they would implement this. And they are the ones who should care about this anyways. So they could basically do that themselves. So if you have Utreexo inside Lightning, we improve performance by a lot. And with Floresta, which is my project, we can achieve the dream of having a full Bitcoin node and a full Lightning node running on your device. So you don't need to like poke random Electron servers on the internet to get your balance or things like this, because we can do that locally. For your wallet, we use BIP158 compact block filters, and then for like channel out points, we use Utreexo. This can be bundled in like one application. Floresta is a library that you can bundle or other stuff. The one we use in the hackathon, it was like a BTK wallet, basically, with Floresta running on the same binary. So it's the same binary you run, like you just open it up, then node spins up, the BTK wallet as well, so you can just like use it on your mobile, like just like that, just like opening an application. And then most of the like update improves, skip improves would be in the Bitcoin side, like the Bitcoin node side. So for example, if you're using Floresta, or we plan to have Utreexo in Bitcoin Core, like short period of time. So Bitcoin Core would keep them for you. So if you're like the implementation, you wouldn't need to worry about doing all the Utreexo stuff. And for the stuff that you do need to like handle the proofs, deserialize and serialize them, we have libraries in Golang, Rust, and we are looking to expanding this into more libraries, more languages. So yeah, that's it. That's how you make Utreexo in Lightning. If you have any questions.
Hey, yeah, great project. I played around with it, not completely successfully, but I did like the ideas, and I just wonder how could it replace like an other Electrum server in terms of speed of like lookup of a large wallet, like with a couple of 100,000 addresses to track. I just wonder,
yeah.
what does the design help in that, or it would be slow or big or something?
It will certainly be slower, because the Electron server, they have indexes to like look this up. We will need to go through the compact block filters and download a lot of blocks. Usually, the public I'm going for with Floresta is like more like the end user that have like small wallets, so they can like have like hundreds or thousands of addresses. That is like easier to handle. Hundreds of thousands, I guess it's harder, especially if you need to rescan like with filters. If you set up the wallet and then do IBD, I guess it's fine. But if you do the rescan with filters, I'm pretty sure that would be worse in performance.
So that what is the difference if I just check one wallet, you know, just a normal user wallet, how much does that take to kind of, you know, build its database?
If it's a day-to-day wallet, like a user wallet that has at most a few thousand UTXOs, that's very, very fast. It's like a couple of minutes at most to figure out what do you need to download and store. It gets harder when I actually tried. I took like a Binance wallet, something like this, with like hundreds of thousands of UTXOs. Yeah, it takes like way more, and it also makes a lot of more network requests. You waste most of the time doing networking stuff, like asking for blocks. I would put in my experiment was like 40 minutes to get the full wallet. It's faster than Core, by the way. And I guess now Core is doing compact block filters as well. But Core used to do this thing where you go like through every single block. We don't do this. We do a smarter way, which is the compact block filter. So it's faster than this, but slower than a full indexer.
And once it's synced, how is the query? Is that is that efficient then? Like when you build the database.
So like the difficult part is the first time you add a wallet. You add a wallet, you rescan for it, and then after you rescan, you found all your transactions. That's like just an API call. Because we keep them, we have a watch on wallet inside Foresta, and we keep them. So we just need to look up the database and give the response back. So it's the same thing as a normal Electrum server. The only hustle is like the first time you add the wallet, because then you need to do a rescan. But after that, it's very efficient.
Yeah, but it's, yeah, great. I mean, it sounds still really good. Like you say 40 minutes, you know, I mean, you sync like an Electrum or like, you know, a Fulcrum Electrum server, and it takes like hours, you know.
Yeah, and that actually pisses me off, because I don't think a user like my mom needs to have a full address indexer, because an address indexer is like a database that has all the Bitcoin addresses that ever receive a transaction, like in the whole history of Bitcoin. Like I just need to look up like a couple of dozens addresses that they have. So why should they? Like I think Fulcrum is like 100-something gigs of disk.
120, yeah.
Yeah, so why? In Foresta, you only care about your wallet. So you're only keeping the transactions that are related to your wallet and nothing else. So this is why it doesn't use a lot of disk and I/O, because it's made for the end user. It's like this is a node that my mom uses, especially because it's embedded into the wallet that you use. So she doesn't need to know this is a node, I need to install this, and then I need to install an Electrum server, and then I need to install, Tailscale to access it from the, no, it's not gonna happen for like everyday people. So we're trying to make something that can give them better privacy, better security, but still I can reasonably present them like, use this app, and they'll use it.
No, I love it, thank you for the answer as well.